Section: Introduction. In this section, we delve into the significance of the learning rate, also known as step size, in controlling the effectiveness and stability of training deep neural networks using gradients. The learning rate is crucially adjusted during training through a specific schedule, involving a warm-up phase where it gradually increases to a peak, followed by an annealing phase where it decreases to zero. It is vital to fine-tune this schedule to achieve optimal performance. Despite ongoing research efforts to understand the best schedule shapes, there is still much to explore. Automatic selection of these hyperparameters using learning rate tuners has gained attention to streamline the tuning process. These tuners draw from traditional optimization theories like inexact line search with Armillo-Goldstein criterion and Polyak step sizes. However, these methods face challenges in deep learning due to the non-convex and non-smooth nature of deep network objectives. The dynamics of sharpness during training can significantly impact the performance of learning rate tuners. Our work aims to address these dynamics by studying classical learning rate tuners and proposing a new method called Curvature Dynamics-Aware Tuning, CDAT. We find that classical tuners often fall short compared to constant learning rate approaches, leading to increased sharpness and decreased learning rates over time. CDAT shows promising results by outperforming constant learning rate tuners in full batch scenarios. It effectively manages sharpness dynamics by dynamically adjusting the learning rate toward stability, similar to a warm-up schedule. Our theoretical model supports the idea that stabilizing sharpness is crucial for successful training in the long term. We suggest that focusing on curvature stabilization rather than solely on minimizing loss can enhance the design of learning rate tuners. By introducing simpler tuners like CDAT, we can better understand and control sharpness dynamics during training. Further experimental details are provided in the appendices for a comprehensive overview. Section Summary. In this section, we delve into the significance of the learning rate, or step size, in training deep neural networks. The adjustment of the learning rate through warm-up and annealing phases is crucial for performance, with recent research focusing on automatic selection of these hyperparameters. Traditional optimization methods like Armillo-Goldstein criterion and Polyak step sizes have been adapted for deep learning, but their effectiveness is limited due to the non-convex nature of deep networks. Our work introduces the Curvature Dynamics-Aware Tuning, CDAT, method, which dynamically adjusts the learning rate to stabilize sharpness, outperforming traditional tuners and highlighting the importance of curvature stabilization over loss decrease in training deep neural networks. Section: Canonical Learning Rate Tuners Failures in Deep Learning. In this section, we examine canonical learning rate tuners failures in deep learning. We first look at a line search method that picks the learning rate to ensure a decrease in the objective function. This method assumes the update direction is a descent direction, which is suitable for simple gradient descent, GD, or similar methods like RMS-prop. The learning rate is chosen to meet a specific criterion, typically with a small constant value. The second method involves selecting the learning rate at each iteration to minimize a quadratic approximation of the objective function. If this quadratic approximation is strongly convex in the learning rate, the minimum of the approximation is reached for a specific learning rate. Analyzing learning rate tuners through curvature dynamics, we find that line searches applied to mini-batches tend to choose larger learning rates than in full-batch scenarios, potentially helping them avoid undershooting the stability edge of the full objective. Theoretical analysis shows that the stabilization effects are due to the interaction between the gradient component and the dynamics of the eigenvalues. When the learning rate is a fixed value, the dynamics show quasi-stable oscillations around the stability edge. However, when the learning rate is a variable, the edge of stability shifts, leading to challenges in maintaining stability. By normalizing variables and introducing a rule for updating the learning rate, we can observe how the learning rate affects the stability edge. If the learning rate continually undershoots the stability edge, it can slow down optimization and disrupt the effectiveness of gradient descent in training deep neural networks. This underscores the importance of understanding tuners that prioritize training at or near the stability edge. Section Summary. In this section, we explore classical learning rate tuners in deep learning. The first method involves selecting the learning rate based on a decrease criterion, while the second method minimizes a quadratic approximation of the objective at each iteration. These approaches, effective for linear models, may undershoot the edge of stability in deep learning, impacting optimization performance. Section: Optimizing on the edge of stability. In this section, we designed learning rate tuners based on our observations to place the optimizer on the edge of stability. We explored a tuner that can operate slightly below and above the edge of stability to take advantage of nonlinear stabilization. Instead of minimizing a quadratic approximation like in the classic tuners, we aim to set the learning rate on the edge by finding the largest value that ensures the approximation is smaller or equal to the original function value. This condition is met when the function is convex and the descent direction aligns with the eigendirection associated with the largest eigenvalue of the Hessian matrix. By aligning with the eigendirection, we derived a rule for the learning rate. We introduced the curvature dynamics-aware tuning (CDAT) rule, which allows us to adjust between a greedy approach and being on the stability edge. The CDAT rule considers information from all eigenvalues of the Hessian matrix and can be used with various base optimizers. We observed that using an exponential moving average, EMMA, for estimating certain quantities is beneficial, especially in stochastic settings. The CDAT rule can be applied in a stochastic setting by considering mini-batches. However, challenges arise due to the variability in the overall objective caused by individual mini-batches. The optimal scaling factor for the on-edge rule may vary with the batch size. We found that integrating an EMA into the estimation process can help in selecting the optimal scaling factor. Additionally, the benefits of the on-edge rule are less pronounced in the stochastic regime compared to deterministic settings. Section Summary. In this section, we optimize the learning rate tuner to position the optimizer on the edge of stability, allowing for exploitation of nonlinear stabilization. By introducing the curvature dynamics-aware tuning (CDAT) rule, we can interpolate between greedy and on-edge behaviors, with a focus on the behavior near the on-edge scenario. The CDAT rule proves advantageous as it considers information from all eigenvalues of the Hessian matrix and can be applied in stochastic settings, showcasing its sensitivity to various optimization scenarios. Section: Modeling CDAT dynamics. In this section, we find that the classical optimization framework falls short in fully explaining the advantages of CDAT. To delve deeper, we simplify the model to grasp the combined dynamics of the learning rate and sharpness in CDAT. By approximating the gradients around a stationary point where the gradient of the function is 0, we can express the learning rate in CDAT as a function involving the matrix H and the difference between the current point and the stationary point. When considering a scenario where the matrix H has two eigenvalues, denoted as lambda and nu, with lambda being greater than or equal to nu, the CDAT learning rate varies between a minimum value and a larger value based on the ratio of projections onto the eigendirections associated with lambda and nu. This learning rate adjustment mechanism allows for learning rates both above and below the expected overshooting (EOS) threshold. By extending the model to include dynamics in the orthogonal subspace, we can gain further insights into the behavior of CDAT. The model reveals two significant behavior regimes. One where certain parameters increase and then decrease, resembling the normal EOS case, and another where a specific threshold triggers a decrease in a ratio, leading to an increase in a parameter according to a defined rule. Numerical simulations based on this model indicate that CDAT tends to drive a certain parameter closer to a specific threshold, especially when influenced by eigendirections corresponding to smaller eigenvalues. However, it is important to note that this model has limitations in fully capturing all aspects of CDAT's behavior, such as predicting extreme sharpening or divergence in certain cases. Despite these limitations, the model provides valuable insights into the intricate dynamics of CDAT.